Evaluating your machine learning algorithm is an essential part of any project. And in order to evaluate a model, so first understand the output class of the algorithms. If we have classification problems, then we use two types of algorithms, which is dependent on the kind of output it creates. The first being the class output, which the algorithms like SVM or KNN, they create a class output. For instance, in a binary classification problems, the output will be 0 or 1. However, today we have algorithms which can convert these class outputs to probability, but these are not really well accepted. And the second is the probability outputs. The algorithms like logistic regression, random forest, gradient boosting, etc. They give the probability outputs, and converting probability outputs to class output is just a matter of creating a threshold probability. In case of regression problems, we do not have any such inconsistencies in the output, so the output is always continuous in nature and requires no further treatment. So let's start with some of the most important, easy to understand metrics to begin with. Remember that we can choose a metric based on the type of the problem and the machine learning algorithm used. So let's start with the classification accuracy. The classification accuracy is what we usually mean when we see the term accuracy. It is the ratio of the number of correct predictions to the number of input samples. It works well if we have equal number of samples belonging to each class. It's great, but it gives us a false sense of achieving very high accuracy. The real problem it arises when the cost of misclassification of the minor class samples are very high. So it's like if you're dealing with a rare but a fatal disease, then the cost of failing to diagnose the disease of a sick person is much higher than the cost of sending a healthy person to more tests. The log loss or the logarithmic loss, it works by penalizing the false classifications. It works well for multi-class classification. And when working with this, the classifier must assign probability to each class for all the samples. So suppose that there are n samples belonging to m classes, and the log loss will be calculated by the formula as given. Remember, the log loss has no upper bound and it exists on the range of 0 included to infinity. The log loss nearer to 0, it indicates higher accuracy, and away from it indicates lower accuracy. In general, minimizing log loss, it gives greater accuracy for the classifier. And you must have come across log loss if you have participated in some Kaggle competitions or solved some problems over there. It's very commonly used. Then we can also have the mean absolute error, which is the average of the difference between the original values and the predicted values. It gives us the measure of how far the predictions were from the actual output. However, they don't give us any idea of the direction of the error, that is, whether we are predicting the data or over predicting the data, and it's represented mathematically by the formula as shown. The mean squared error, MSE, is quite similar to MAE. The only difference is that the MSE, it takes the average of the square of the difference between the original values and the predicted values. Also, the advantage of MSE being that it is easier to compute the gradient, whereas MAE, it requires the complicated linear programming tools to compute the gradient. So as we take the square of the error, the effect of large errors become more pronounced than the smaller errors, so we can focus more on the large errors, and it's given by the formula as shown. Derived from this is the RMSE, root mean squared error, which is one of the most popular evaluation metrics, and it is used extensively in regression problems. It follows the assumptions that the error are unbiased and follow a normal distribution, and it is given by this mathematical equation. However, there are few key points to consider when working on RMSE. The power of square root, it allows this metric to show a larger number of deviation. The squared nature helps to deliver more robust results because it prevents the cancelling of the positive and the negative error values. So it displays the magnitude of the error terms basically. If you have more samples, then reconstructing the error distribution using RMSE is considered to be more reliable. But RMSE is highly affected by the outlier values. Hence, make sure that you have removed outliers from your dataset prior to using this metric. And as compared to mean absolute error, the RMSE gives higher weightage and punishes large errors. R square, it determines how much of the total variation in y, which is the dependent variable, is explained by the variation in x, the independent variable. And mathematically, it is written by this formula. The value of the R square is always between 0 and 1, where 0 means that the model does not explain any variability in the target variable, and 1 explains the full variability in the target variable. Next, we talk about the adjusted R square. Why do we need that? Because the only drawback of R square is that if we have new predictors added into a model, R square value, it increases or remains constant, but it never decreases. So we cannot judge the complexity. We cannot judge that by increasing the complexity. So that's why we use adjusted R square. And this was also a question that was asked to me in one of my interviews. Why do we use the adjusted R square and all? So this adjusted R square is a modified form of R square that has been adjusted for the number of predictors in the models. It incorporates models' degree of freedom, and it only increases if the new term improves the model accuracy, and it is given by this formula as shown.